Hello, I'm Jalen Jones, and today we'll be talking about the ideal free distribution model. The ideal free distribution model predicts that in order to minimize the resource competition animals have with each other, a population may distribute itself across multiple resources so that it's evenly distributed. Both the availability of resources and the presence of other animals are very important factors and variables when considering if this model is being applied, as it can be used to describe equilibrium distribution between the abundance of organisms and the amount of resources. There are several predictions associated with this model. 1. Individuals will settle in habitats according to fitness payoffs. 2. Habitats of higher quality will support the most individuals. And 3. Eventually, all of the individuals will reach the same fitness regardless of which habitat they are in. So in this figure, it shows the fitness of individuals by density in habitat A and B. So according to this model, animals in an environment should distribute equally in habitat A and habitat B in order for each individual to have the same fitness. However, in this case, habitat A will have more individuals than habitat B. So therefore, new individuals that arrive to this region should choose habitat A, seeing that it will give them maximum fitness. But over time, as the density of habitat increases in habitat A, the fitness will decrease for these individuals. And at the point indicated in the graph, we see that habitat B will reach a point where it is able to provide the same fitness that habitat A does. Therefore, new arrivals could choose either habitat to reside in. It is important to note that despite having two different population densities between two habitats, they can have the same fitness. So we could see at these two blue dots, while they have different population densities, their fitnesses are the same. So these graphs typically must show a linear relationship based off the densities. So as habitat B fills up, the animals will be seen to move to habitat A, resulting in an isodar. This will display a habitat isodar for a species of animals in two habitats. The straight line shows the equal fitness in both habitats. So now we will go over a case study regarding black-capped birds, but first we must know that there are specific criteria in order to fit this model. 1. Individuals must attempt to maximize fitness. 2. Individuals are equal competitors. 3. They can freely move at no cost. 4. Their habitat locations must differ in resources. 5. Their fitness of individuals is negatively density dependent. And 6. The plot of the densities of the two habitats against each other must show a linear relationship. So to provide some background, black-capped birds prefer to nest near streams as their main food source is aquatic insects who live within these streams. So we will have two habitats. Habitat A will contain streams with 10 resident birds where there is high interspecific competition, and habitat B containing a woods habitat with 1 resident bird containing low interspecific competition. The results show that when black-capped birds' density was much lower, fitness was much higher in those regions. So implications can be made that any new individuals would have higher fitness living in habitat B rather than habitat A. To discern if this creates an isodar, we plot the two graphs against each other by taking the different fitness levels and population densities of both habitats. As we can see from this, it creates a linear relationship. So for this case, I would say that it did fit the model as individuals were able to freely move at no cost. The habitats did differ from one another. Fitness was shown to decrease as the population increased, and the plot of the densities did show a linear relationship. It is important to note that while the two criteria of this model were not specifically given, we can assume that they were met.